Do you know stress is different in a beam and in a column? In this lecture, I will discuss four main topics: direct stress in axial members, stress in bending members, centroid of the section, and second moment of area. When I am bending a beam like this, there's a lot of bending. But if I'm turning it to 90 degrees and if I'm trying to bend it now, it is not bending. Why is it that the same cross section is bending in one direction but not bending in other direction? This is due to second moment of area. In today's lecture, I will talk about second moment of area. Hey friends, if you're new here, I am Dr. Javed Qureshi, a senior lecturer at a London university. On this channel, we explore technical and human skills to help us lead more productive, happy, and examine life. In this lecture, I will discuss a very important topic, which is section properties of any cross-section. Section properties are absolutely critical when you are designing any civil or mechanical engineering system. This is how my today's lecture is organized. I will be talking about four important topics today. First is direct stress, which means that when we apply tension or compression to any member, how do we find out its stress? Second is engineer's bending equation or flexural formula. What happens if we had to find out stress when we are bending an element? Centroid of the section is absolutely crucial. When we are trying to lift something, we ensure that it is lifted at center of its mass, otherwise it will be kept hanging. Fourth is second moment of area. If I'm bending a beam like this, in this position, you can see that this is bending. But if I'm turning it to 90 degrees, now if you try to bend it, the cross-section is quite stiff. What causes that behavior? This is because of second moment of area. First, direct stress for tensile or compressive model. I have this sample, similar to this one. When you hold a bar or a dog bone sample in a tensile testing machine, and when you try to pull it, what happens? So it is clamped at top and bottom. Then we apply tensile force. And this is the cross-sectional area. This is the bar. So cross-sectional area is pi r square. Stress is equal to force over area. So whatever force we are applying, if we divide it by area, it will give me stress. If it can sustain more stress, it means that the material is very strong. For example, if we are talking about steel, steel will take more stress, like 275 Newton per millimeter square. If I'm talking about concrete, certainly in compression, it is going to take about 30 Newton per millimeter square, but in tension, it is very weak. It will take about 3 Newton per millimeter square. And unit, as I mentioned, is Newton per millimeter square. Now, how about if I have a beam? If I am bending an element, can I use the same formula, force over area, to find out the stress? The answer is no, because bending behavior is different to applying tension or compression. Most of the structural members, they are not subjected to direct tensile or compressive stress. Instead, they are subjected to bending stresses. Engineer's bending equation is used to work out stress distribution across the member. For the entire depth of the section, we can find out the stress distribution. This is flexural formula or engineer's bending equation. This is one of the single most important equation in civil, structural, and mechanical engineering. If you know this equation, you can pretty much design any system. It is M over I is equal to sigma over Y is equal to E over R. The question is what these terms are. So we will see it in a minute what these terms actually mean. The first is M. M is moment, for which unit is Newton into millimeter or kilonewton meter. It's normally taken as the maximum bending moment. So when I'm applying loading over here, if it is a point load, it will cause maximum bending moment. I is second moment of area. It is a geometric property of the section and it depends on the shape and its dimensions. Sigma is equal to stress, which is Newton per millimeter square. It is worked out at a position of applied moment at any distance from centroid of the section. So centroid is critical. So for finding out stress, we need to find out the centroid. Y is distance in vertical direction. It is distance from centroid to the point where stress is to be found out. For example, if I have this simply supported beam, if a central point load is applied to this beam, then what will happen to this beam? What do you expect? If I have a beam and if I'm applying a point load, what will happen? Certainly it will bend. So let us see when load is applied, how the beam is bending. Load is increased. You can see beam is bending. Again, I'm increasing the load. Again, I'm increasing the load. You can see beam is bending and bending moment diagram is taking this shape. In a sense, what is happening is that bottom of the beam is stretching and top of the beam is in compression, or it is reducing in size. As you can see with the help of these arrows, that top is compressing, bottom is stretching. And what you can see over here, one other important thing, which is neutral axis. Neutral axis is neutral. It means that it does not have either tension or compression. It means that it does not have stress. Stress is zero at neutral axis. And neutral axis passes through the centroid of the section. Now, how do we find out this distance y in vertical direction? So we cut a section. When we cut a section, it will look like this. This is the axis which passes through the center of the section. And then again, we have y-axis. The point where both these axes are meeting is termed as position of centroid. Let us see how we can plot stress distribution. So first is compressive stress. From center, it is y1 distance away, and it will have the maximum compressive stress denoted by sigma 1. Equally, on the tension side, it is y6 or sigma 6. Both stresses are equal if a material is homogeneous. So for example, for steel, this will be the behavior. But for concrete, concrete is really very strong in compression, but it is really very weak in tension. Its tensile capacity is about 10% of its compressive capacity. Let's plot compressive stress at sigma 2, another location, y2 slightly less than y1. And let's plot at sigma 5 on tension side, y5. And then I have y3, sigma 3, y4, sigma 4. What do you think stress will be at a point where we have centroid? It is going to be 0. So stress at this point, which is here, is 0. And this point is termed as neutral axis. So neutral axis is an axis which passes through the centroid of the section, at which the stress is 0. That's why we term it as neutral axis. E is Young's modulus or elastic modulus. Now, how do we determine Young's modulus? It is the material property and it relates stress to strain. Now, what is strain? Strain is a measure of deformation. Strain, in simple terms, is change in length per unit length. Practically, we can determine Young's modulus. For very strong materials like steel, Young's modulus is high. For concrete, Young's modulus is low. Typical Young's modulus for steel is about 210 gigapascals. And for concrete, it is about 30 gigapascal. Now, how do we determine E? What we do is that we put a sample, for example, if it is steel, in a tensile machine, and then we try to pull it up. We see that how much load is applied. Up to point A, load is applied, and the load versus strain curve is fairly linear. And then at point B, it starts to yield. At point C, it starts to yield. And again, it remains static for up to point E. This is termed as yielding. And then strain hardening starts at point F. It attains ultimate stress, and then after that gradually necking happens. Necking means that the reduction in size of the specimen over here. If I pull this specimen, it will reduce in cross-sectional size over here. And E is stress over strain in elastic range. So this is the linear region where we can find out E. R is radius of curvature of member under a specified loading. So if I have this member, if it is bending like this, so this is simply R. Stress for a simple member, from here I can say that stress is equal to my over I, because I can, by cross multiplying, I can bring this y over here. I can say that stress is equal to my over I, where m is moment, y is distance from centroid to the top fiber or wherever you want the stress to be determined. I is second moment of area. The way I remember this formula is stress is equal to my over I. So my is me as well, I is me as well. This is how you remember this formula. Now, what section properties are we going to discuss? So first is area, second is centroid, and third is second moment of area. So area is very simple. So area depends on size and shape of an object. If you have rectangular object, simply you multiply its width with its height. If you have a triangular object, then you will say that half width into height. If you have a circular object, then simply you say that area is equal to pi over 4d square, or simply you can say that pi r square. How do we find out area of compound shapes? Area of T section, simply we will divide this T section into two equal areas, and in that way we will be able to find out the total area. Here, divide it into two parts, area 1 and then area 2, and simply add these two areas up, and that way you'll be able to find the total area. Second is centroid. What does it mean by centroid? Centroid is simply center of area of the section. If a section is symmetric and simple, for example, rectangular section, it would be at its center. It is very simple to find out. But if a section is a compound section, it is a combination of different sections, then certainly it's a bit difficult to find it out. Bending happens about the longitudinal axis through centroid. This is vertical datum axis or y datum, horizontal datum axis. We have a section, a rectangular section. The position of centroid would be at the center of the section. Now, how to find out centroid if we have sections other than rectangular sections? So for rectangular sections, simply in vertical direction, we say that d over 2. In horizontal direction, we say b over 2. For circular section, again, it is very simple. We simply say that diameter divided by 2 or a radius. It will give us the center of a circle. But how about a triangular pattern? For a triangular pattern at 90-degree point, you will see that it is b over 3. It is 1/3 of that dimension. At the longer side, you will have 2/3 of that dimension. So 2h over 3 at the top and 2b over 3 at the bottom. Now, how to find out centroid of compound sections? We have this section where we have y datum and we have x datum. We have this formula, x bar is equal to distance from y datum to the centroid in horizontal direction, where y bar is distance from x datum to centroid in vertical direction. So how do we find it out? We divide the element into number of areas, then we find out area of each element, and then we find out its location from datum x. And simply how many number of areas you have, you multiply it with their x and y, and then you divide it by total area. So that's how we work out x bar and y bar. For example, if you have this section, first step is to find out datum x's, x and y datum x's. And the way I will do it is I will take the extreme bottom point of the section and I will say X datum. I will take extreme left side of the section and I will say Y datum. Now, everything will be in reference to X and Y datum. So first is centroid of part 1. I take half of the horizontal dimension and half of vertical dimension, and simply I find distance from center of this green rectangle to the X datum. That would be my Y1. From center of A1, area 1, to the left point will be my X1. Now area 2 will be, this is the centroid of part 2. From center of this point to the datum, I call it as X2. From center of this point to X datum, I call it as Y2. Once I have X2, Y2, X1, Y1, then I can find out X bar and Y bar. Now this is centroid of the compound section, which is here. Now how do we find out in formula? We will multiply A1 with X1 and A2 with X2 divided by A1 and A2. In that way, we will find out X bar. And similarly for Y bar, we will multiply A1 with Y1, A2, Y2, and A1 and A2. Now it really depends on number of areas. If you are dividing a compound section in number of 4 areas, then you will have A1, Y1, A2, Y2, A3, Y3, and A4, Y4. Similarly divided by 4 different areas. So it depends on number of areas. If area is symmetric about an axis, centroid must lie on that axis. What does it mean? A channel section, is it symmetric in Y direction or is it symmetric in X axis? I would say probably it's symmetric in X axis. So here you can see that centroid lies on this X axis because it is symmetric in that direction. In Y direction, it is not symmetric. If area has 2 axes of symmetry, then the position of centroid lies at intersection of axes of symmetry. So here I have I section, it's symmetric in X and Y direction, and centroid must lie at this point, which is intersection of these 2 axes. Second moment of area. The unit for second moment of area is millimeter power 4. I is defined by axis passing through the centroid. If I have this section, I have X axis, I have Y axis. This is the position of centroid, and this is my neutral axis. Load is applied to the section, and this is showing elevation of the section. IXX is bending about X axis. If I have this section, if this axis is X axis, the vertical is Y axis, then if I try to apply loading over here, this is bending about X axis. Bending about Y axis means that if I turn it like this, and then now I apply load, Y axis is a minor axis here. Now you can see that it is bending quite a lot. Second moment of area is moment of area about a known datum. So if I have this element, I have X datum. This is a small area and it is at a distance of h from datum. I will say moment of area about X datum is A times h. So area times h. Second moment of area about X datum will be AH times h, which becomes AH square. Second moment of area I about centroid of most common shapes. So if I have really very simple shape, second moment of area will be for rectangular section, X is passing through the centroid and Y is passing through centroid as well here. Area is B times D. IXX is BD cube over 12. This is the reason you would see that most of the times beams will have higher depth than their width. And the reason is that when you have higher depth, then second moment of area is more. When second moment of area is more, they will have more bending capacity. They will have less deflection. To demonstrate this, I have this ruler. Depth is 20 millimeter and its width is about 2 millimeter, depth is quite high. In that way, when I'm trying to bend it, it's very difficult to bend. But if I'm turning it like this, now its width is 20, depth is 2 millimeter. Now it's bending really very easily. How about a triangular sections? Area is half BH, IXX is BH cube over 36, IYY is HB cube over 36. How about a circular section? For a circular section, X and Y axes, area is pi over 4 d square or pi r square, IXX is pi d power 4 over 36. Pi d power 4 over 36. IYY and IXX is same. Circular section is the most effective section because its major and minor axis second moment of area is same. Second moment of area about a datum at a distance from centroid. Now, how about if the datum is not passing through the centroid? In this case, I have x-axis and y-axis. X-axis of the section is at a distance from my datum axis. ICG is the second moment of area about centroid of the section. I about datum axis, which is x-axis, is equal to ICG, which is second moment of area of the section, plus AH square. ICG is second moment of area about its centroid. A is area of the section. H is distance from X about which second moment of area is calculated. This is termed as parallel axis theorem. When the datum axis does not lie at the centroidal axis, then we use parallel axis theorem. Or when we have compound sections, then we utilize this parallel axis theorem. Second moment of area of compound sections. IXX is equal to summation of individual IXX plus summation of A y bar minus y, where y bar is the centroidal dimension and y for a particular section. IYY, on the other hand, is equal to summation of IYY plus summation of A x bar minus x whole square. This is making use of parallel axis theorem. And in a while, you will see that how do we use these formula for compound sections. The relationship between centroid of compound section and centroid of parts. For example, if I have this section, first thing I will do is I will define the datum, and datum will be extreme bottom point and extreme left point. And I will divide it into three areas. First, A1, A2, and A3. For first one, center is this one, which is X1 and Y1 away from datum axes. And this is centroid of part 1. For A2, this is the centroid. It is X2 and Y2 away from datum axes. This is termed as centroid of part 2. For third area, this is the centroid, and it is X3 and Y3 away from datum axes. And this is centroid of part 3. Now, this is centroid of the compound section, which is X bar away from Y datum. And how do we find out X bar? We use this formula. And then we have Y bar. We use this formula to find out the centroid. So first thing is to find out centroid. This is centroid of compound section. IXX is summation of IXX plus summation of A y bar minus y whole square. This is how we find out second moment of area of compound sections. For IXX, we will find out y bar. So y bar minus y1 is this distance, where we subtract y bar from y1 for individual areas. And we repeat the process for y2, we repeat the process for y3. In that way, we'll be able to find out IXX for the compound section. Now, how about if we have to find out IYY? In that case, we'll find out X bar minus X1, where X bar is distance from centroid to the Y datum, and X1 is distance from center of A1 to Y datum. In that way, we will repeat the process for A2 and A3 and we'll be able to find out IYY. These are the books that I have referenced to prepare these slides.